Welcome to all of you. This is lecture 2 on graph theory, second lecture, graph traversals and connectivity. First, we define walk. A walk W in a graph G is a triple V E gamma is a finite alternating sequence of vertices and edges beginning and ending with a vertex. This W V0 E1, V1, E2, V2, and dot 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 En, Vn, starting with vertex V0 and ending with vertex Vn, where gamma Ei equal to the set Vi minus 1, comma Vi. The edge Ei is incident to the vertex Vi minus 1 and Vi for all 1 less than equal to I less than equal to n. V0 is called the initial vertex and Vn is called the terminal vertex in the walk W. Here, the length of the walk, that means the total number of edges, steps it contains, counting repetitions also. So, in the sequence above, this V0 to Vn, so E1 to E2 to En, so length of the walk is n, and walk of length 0 is just a single vertex, no edge here, the isolated vertex, so length is 0. An open walk means the walk where starting and ending vertices are different. Is V0 not equal to Vn. And where closed walk, the sequence starts and ends at the exact the same vertex, that is V0 equal to Vn. A walk is completely unrestricted both vertices and edges. And edges and both and vertices can be visited and traversed multiple times throughout the sequence. No restriction uh, for vertices or edges. And this is the example of a walk. This vertex V1 to V2 by the edge E1. Next, V2 to V3 by the edge E2. And this is the same edge E2 and return to V1, E1. So, this diagram is a closed walk because we start from V1 and end terminating with V1. So V1 sequence is this: V1, E1, V2, V2, E2, V3, E2, V2, E1, V1. So here E1, E2, V2, E1 are all repeated. This is the walk, actually this is the closed walk of length 4, because here E1 twice and E2 twice, so length of the walk is 4. So vortex trajectory from V1 to V2 to V3 to V2, again V1, and the closed walk of length 4. The walk demonstrates full repetition. The vertex V2 is visited multiple times, here V2 and V2, and the edges E1 and E2 are traversed back and forth across their original paths. And the unused elements, the V4, its incident edges are part of the overarching graph background, but they are not traversed by walk sequence W. Thus, they are rendered as inactive component. Is the graph here? This inactive component is H and this vertex V4, but this is not a part of the walk closed walk here. Next definition, trail. A trail T in a graph G is a walk in which all edges are distinct. Formally, a walk T equal to V0, E1, V1, E2, Vn is a trail if and only if Ei not equal to Ej for all 1 less than equal to I less than j less than equal to n. The vertices in a trail are allowed to repeat. So, only restriction here on the edges. All edges are distinct, but vertices allowed to repeat. Now, key properties of a trail. Edge constant. No edge appearing in the sequence can be repeated. Every step must be traversed a completely fresh edge. Vertex flexibility. An edge must be unique. Vertex may be visited multiple times. A trail can cross its own path at node. Circuit, actually, is the closed trail is called a circuit where V0 equal to Vn. So circuit is nothing but a closed trail. This is the example for a trail. The trail of length 5 starting from V1 to V2 to V3 to V4 to V2 and V4. So here this intersection, this V2, the directed edges trace intersection loop at V2. So this V2 repeated and this starting from V1 and ending at V4, V5, sorry, V5. So this is the open trail. This is the open trail. This no is here repeated, but vertex V2 is repeated here. In the above structure, the sequence of the this trail T is V1, E1, V2, E2, V3, E3, V4, E4, V2, E5, V5. So length of the open trail is 5 because E1, E2, E3, E4, E5. There are 5 edges. And vertex trajectory is this V1 to V2 to V3 to V4 to V2 via E4 and V2 to V5 via E5 by this figure. V1 to V2 by E1, V2 to V3 by E2, V3 to V4 by E3 edges and so on. Walk validation, it remains a valid walk because it maintains a continuous alternating sequence of valid incident steps. Trail validation, it is a true trail because the edge subset E1, E2, E3, E4, E5 consists entirely of distinct elements. Nothing is repeated here. So no repetition allowed for edges. And vertex intersection is the vertex V2 is visited exactly twice, and this is structurally acceptable since vertex reuse is allowed in trails. Next definition, path. A path P in a graph G is a walk in which all vertices are distinct. Formally, walk P is the sequence V0, E1, V2, E2, En, Vn. Is a path if and only Vi not equal to Vj. For all 0 less than equal to I less than j less than equal to n, hence all edges ek in this walk P are also necessarily distinct. So, vertex and edge, no vertex in the sequence can be visited more than once. Trajectory never crosses itself, and because no vertex can be repeated, it is structural consequence that the all edges within the path also distinct. So vertex and edge both are distinct here. No repetition allowed for vertices or edges. Cycle, in particular case, the closed walk where V0 equal to Vn, this closed walk uh, is called a cycle. This is the example. This is the example from this graph. This is V1 to V2 to V3 to V4. This is the open path. This is the open path. Open path, and the highlight here, larger graph background. The length of this path 3, because E1, E2, E3, 3, and no vertices or no edges here repeated. This is the sequence V1, E1, V2, E2, V3, E3, V4. We grab this containing the vertex set V, as illustrated in this figure 14. This, sorry, we contrast two sequences to isolate the concept of the vertex uniqueness. Valid path example: sequence V1, V2, V3, V4 constitute true path. Every node every node or every vertex appears exactly once in the tracking order. And non-example trail, the sequence V1 to V2 to V3 to V2 and V5 is not a path because V2 is visited twice. So by this sequence V1 to V2 to V3, V1 to V2 to V3, and again V2 to V5, V2 to V5. We travel from this to this. So if we travel from this V1 to V2, V2 to V3, and again V3 to V4, V2, and V3 to V5. This is not a path, because here the hierarchy of graph movement. Here path is a subset of trail and trail is a subset of walk. So by the set diagram, Venn diagram, these walks, this trail subset of walks, and path is also a subset of trail and subset of walks. And structure for walk, edges may repeat, vertices may repeat, but for trail, edges distinct, vertices may repeat, path, edges distinct, vertices also distinct. Next, we define circuit. Circuit actually is the closed trail. The circuit C in a graph G is a non-trivial closed trail. Formally, it is a trail of positive length n greater than equal to 1 that begins and ends at the same vertex, and all edges are distinct, but vertices may repeat within a circuit. This is the circuit, the closed trail. So initial and terminal vertices are same, and this the edges are all listing. So ei not equal to ej for all 1 less than equal to I less than equal to less than j less than equal to n, and the minimum length L n of the that is the length means the total number of edges. For a valid circuit, for simple circuit, minimum number of edges is 3, so n greater than equal to 3. Because loops are parallel edges are forbidden here. To return to the starting vertex without repeating an edge, we must visit at least 2 other vertices. So n greater than equal to 3. So this is the list number 3 for the simple graphs for describing circuit. Circuit for multigraphs, parallel edges are allowed here. We can travel from the vertex A to B via edge E1 and return to A via completely different parallel edges E2. So n greater than equal to 2. So circuit for multi-diagram, this vertex A, this vertex B. So this is the, say, E1, and this is the E2. E2. So for multigraphs, this vertex A to B and again back to A. So number of length is 2, E1 and E2, for creating a circuit. Next, circuit for pseudographs. Pseudographs, graphs with loops and are allowed here. So loops are allowed here. So loops are allowed here. So this is the vertex V, and this vertex V, this is the loop, this say E. So for this pseudograph, this is the length single edge, this single edge E can connect a vertex directly to itself, creating a valid circuit of length exactly 1, because the edge 1. So n greater than equal to 1. So for pseudograph, n greater than equal to 1, and for circuit for multigraph, n greater than equal to 2, and circuit for simple graph, n greater than equal to 3. And next, some properties of circuit: the closed structure, the closed work, actually is the closed work, V0 equal to Vk, meaning that the traversal begins and ends at the exact same vertex. Distinct edges, every edges in the sequence is traversed at a most once, Ei not equal to Ej, for all I not equal to J. Vertex repetition, unlike a cycle, intermediate vertices can be revisited, example crossing its own path at structural intersection point. So the intermediate vertices can be revisited in the circuit. Subcycle decomposition, any circuit that revisits an intermediate vertex can be broken down and decomposed into collection of smaller edge disjoint cycles. If a graph contains a self loop connecting the vertex itself, valid closed trail edge also can be formed using only one vertex and one edge, already discussed here. So this is the example of a circuit starting from V1, V1 to V2, V1 to V2 to V3, and next V4, next V2, next V5, and come back to V1. So this is the circuit. Closed trail. Here vertex V2 is repeated here, but no edge is repeated here. And this V6 is not is a part of the circuit. This is the circuit closed trail, and we decompose this circuit by these two, this V1 to V2, V5, this one, and this V2 to V3 to V4, again V2. This we can decompose this subcycle decomposition. Any circuit that revisits an intermediate vertex can be broken down and decomposed into a collection of smaller edge disjoint cycle. Next definition, cycle is the closed path. A cycle C in a graph G is a non-trivial closed path. Formally, it is a path of positive length n greater than equal to 1 that begins and ends at the same vertex. All internal vertices and all edges must be distinct. Because it is a path, only the first and last vertices are equal. So V0 equal to Vn, and with Vi not equal to Vj for all 0 less than equal to I less than j less than equal to n minus 1. Similarly, we can find the minimum length n for simple graphs, multigraphs, and pseudographs. And for circle, minimum length is greater than equal to 3n, and multigraph n greater than equal to 2, and for pseudograph n greater than equal to 1 for creating a cycle. Next, properties of cycle. Vertex edge equality. Number of vertices, the number of edges are equal, and every single vertex contained within a cycle has uniform degree exactly 2. So degree vertex of all vertices degree equal to 2. It is a 2 regular graph. Connectivity status. Every cycle is a connected structure containing exactly one enclosed regional boundary or face when mapped onto a planar space. We will discuss later. This is the planar graph. Minimal list dependency. Removing any single edge from this cycle destroy the closed loop structure, instantly transforming the remaining subgraph into a simple linear path. If we remove some edge from the cycle, this is the example. The cycle, this is the closed path starting from V1 to V2 to V3 to V4 and V1. So this is the closed path highlighted in green, and the surrounding dashes, this V5, V5, what is this called, our outer branches are excluded from the cycle of this total graph. They're excluded from the cycle. We only construct the cycle by this E1, E2, E3, and E4. So length of this cycle is 4 here. And V1 is the starting and ending, terminating vertices. You can start from V2 also. And the degree of V1, V2, V3, V4 are all 2. Next, inclusion relationship. Every cycle is circuit, but circuit is not necessarily a cycle. So cycles is a subset of circuit. So cycles implies this circuit if all intermediate vertices are unique, all edges are guaranteed to be unique. But circuit does not imply cycle. A circuit can revisit intermediate vertices, example crossing its own path at the central node, which is strictly forbidden in a cycle. So a circuit cannot be cycle, but a cycle is also a circuit. Next is the circuit and versus cycle. Some properties. Circuit, actually this is the closed trail. Cycle is the closed path. Both terminal and starting and terminal vertices are same for circuit and cycle. Edge repetition forbidden. All edges are distinct, and also in cycle also edge repetition forbidden. But the main difference is that in circuit the vertex repetition allowed, whereas for cycle vertex repetition is forbidden. No vertex repetition allowed in cycle. And for simple graph, minimum vertices greater than equal to 3, and also for cycle minimum vertices greater than equal to 3. Internal loops can contain subcycle, strictly a single loop. By circuit from the central vertex V2, we can decompose these two subcycles. Circuit implies cycle, but circuit does not imply cycle, but cycle implies circuit. Already we discussed here. Cycle implies circuit. This is the flowchart for the This is the vertex edge repetition sequence, input sequence V0 to Vn, and this is the first we check these consecutive pairs connected by the valid edges. Yes, so status is walk. No invalid sequence. Next, check if every edge is traversed exactly once. Yes, so this is a trail. No. Next, check is it closed? The initial and terminal vertices are same. Yes, this closed walk. No, this open walk only. Next, from trail, check each every inner vertex is visited exactly once. Yes, so this is path. No, check again. Is it closed? Initial and terminal vertices are the same. Yes, this is the closed trail. That is, the name is circuit. Otherwise, it is open trail. And from path, is it closed? That is terminal V0 equal to Vk. Yes, this is the closed path. That is cycle. No, this is the open path. This is the flowchart for walk, trail, path, and the circuit and cycle. Now, we here uh, draw this diagram for open walk and closed walk. Here, open walk only, starting from V1 to E1 to V2 to E2, V1, E3 to V3. So here age E1, this age at same age E1, from V1 to V2 E1 and V2 to V1 also E1. So E1 repeats and starts not equal to end. Starts from V1 and the end terminal vertex is V3. So this is the open walk only. And this from V1 to V2 via E1, V2 to V3 via E2, V3 to V2 via E2, V2 to V1 via E1. So edges repeat and starting vertex and terminal vertex same. So this is the closed walk only. Next, trails. Open trails versus closed trail. Open trail from V1 to V2, V3 to V1 to V4. So here the starting vertex V1 not equal to the terminal vertex V4, and here no edge repetition here. So all edges are distinct. This E1, E2, E3 and E4. So this is the vertex repetition here. This V1 uh, is repeated here. So this is the open trail. And this is the closed trail starting from V1 to V2 to V3 to V1 to V4 to V5 to V1. So starting and ending that is the same, and these no edges are allowed to repeat here. Edges are all distinct, and the vertex V1 is repeated here. The closed trail is the starting and ending, but it's the same. No is repeated here, and the vertex repetition is allowed here. So this is the closed trail, and this is also known as circuit. Next, open path and closed path. The open paths V1 to V2 to V3 to V4. This is the open path because V1 not equal to V4, and this the all vertices are unique. Uh, so edges are also unique here. No repetition for vertices or edges. This is the open path. And for this diagram, this V1 to V2 to V3 to V4 to V1. So the inner vertices are unique here, and starting vertex and ending vertex V1 are same. And this is the closed path, also known as cycle here. Thank you for watching this video.